N ne?
Bunun benzerini biz geçen sene organizasyonunda görmüştük de orada baştaki indeks numarasından sonra şey ekliyorduk.
Organizasyonu ben bilmiyorum ya. Sen benim bilmiyorum. What is the page frame number size? What do I have now? I have the physical memory size, I have the virtual memory size, and I have the page size. Okay? Let's say P is the physical memory size, V is the virtual memory size, okay? And G is the page size. How do you decide on the page frame number size? How many bits are there? What does this do? This gives me the page frame number, right? So how many total page frames are there in the physical memory? How many total page frames are there?
İndeks
Give me a formula.
Physical bölü G.
Yes. It is the physical memory size over the page size. Over the page size. If my physical memory is 32 kilobytes, okay, and I have 4 kilobytes of page size, then 32 over 4 is 8, right? So I have 8 pages. To be able to address 8 pages, how many bits do I need? I need just how many bits? To address 8 pages, how many bits do I have?
3.
Just 3, right? Just 3. That's why we have only 3. Okay? We have only 3 bits here. So this part is, in our case, it was 3. So usually, okay, you tell me, okay, which part is larger? Okay, this one or this one? Okay, which one is larger? Number of pages or number of page frames?
Number of pages.
Number of pages are larger, right? That's the idea of paging. Because I have much larger virtual memory, and my physical memory is smaller, and that's why I'm using paging and virtual memory. I am using some kind of a mapping. That's why some of these are 0, some of them are invalid. So number of pages are larger. In this case, it is the 2 times the number of pages is the 2 times the number of page frames. Okay. So let's move on. This is the structure of the page table entry. The thing is that this approach is so simple, because remember what we said. Okay, we said that our memory is 64, virtual memory is 64 Ks, and our physical memory is 32 Ks. These are like toy numbers, right? Nobody has a computer of 64K anymore. Maybe 30 years ago, these numbers were like realistic numbers, but nowadays the numbers are very large. So the problem is that on PDP-11, this was one of the most popular computers where the Unix system is developed. It has 8 pages of address space. So it was very similar to the example that we used. And so when you have the 8 pages of address space, then that 64 kilobytes of virtual memory is enough. So 16 table entries is good enough. But nowadays modern computers have 1 gigabyte of memory. Okay, 1 gigabyte of memory and page size of 4K. That means that I have 256,000 possible pages. So my page table, this one, has instead of 16, it has 256,000 entries. That's a very large table. And doing this operation becomes very expensive, because this is inside MMU, right? MMU is on the CPU, so it doesn't have large amounts of memory, MMU. 16 registers or 16 element tables, 16 element tables are okay with the MMU. 16 element tables are okay with the MMU. But if you want to put 256,000 table entry table inside the MMU, then your MMU will be very, very expensive. That's why this solution doesn't work. I mean, a simple table, and you are looking up, it doesn't work. Modern computers, they have so many memories, and our page sizes did not grow. Page size is the same, the amount of memory grow, so the number of pages is so large. So we can't have that many MMU registers. So we need a separate page table for each process. That's another problem. I mean, each process has its own page table. If we have a few hundred processes, and each one is needing this kind of page tables, and loading them, unloading them, may be very, very problem. Okay, we can't afford to copy that many MMU registers during the process switches. That would make the process switch even more expensive. It is already expensive. It makes it even more expensive. So this simple solution, table lookup, doesn't work. We need to come up with some other solution. Some people say that let's keep this table instead not on the MMU but on the RAM, okay, on the main memory. If we keep them in the RAM, what would be the problem? Okay, so I can't keep all this data on MMU. Let's keep them in the RAM, because in the RAM I have gigabytes of memory. This is not a very big problem. Okay, this is a very small amount of memory for a core memory. So, but if I keep them on the RAM, what would be the problem?
Slow.
It becomes slow. Why?
Cache is fast.
What?
Cache is fast. CPU'nun içinde daha hızlı.
Niye yüksek sesle söylüyorsun?
CPU'nun içindeyken yani orada tutarsak daha hızlı oluyor.
Well, this is definitely faster if it is on the MMU. But if I keep them in the RAM, that means that every time I need to make a memory reference, I need to go to the system memory more than once, 2 times. When memory access is already slow, and if I do the slow operation 2 times, it would make it much slower. So keeping the page table in the memory is very slow. Okay, an extra RAM access for each memory reference. That's not a good thing. Okay, it's a lot of RAM for page tables, and I mean, using lots of RAM is not a problem because we have enough RAM, but it is slow. Okay, it is slow. But again, as I said before, keeping them on the MMU is expensive. We don't have that many registers. 250. We have 16 is okay. 16 is okay. Maybe 32, maybe 64 is okay. But 256,000 is not okay. Keep them in the RAM, it becomes slow. So I have to find some kind of a solution, in between solution. We are going to keep the table in the RAM, but the solution is something like a cache. We would find the important ones. We would keep the important ones on the MMU, but keep rest of them in the RAM. The solution is okay. These are the problems. The mapping from virtual address to physical address must be fast. If I keep all the page tables on the RAM, it becomes slow. Okay, and if the virtual address space is large, the page table will be large. Okay, I mean, modern computers, the virtual address space is very large. Okay, they are addressing terabytes of spaces. Okay, it's very, very large. So I need a very large page table. But page tables, keeping them on the MMU would be expensive. Keeping them on the RAM would be slow. So the solution is translation look-aside buffer. It's kind of cache for the page tables. Okay, mapping from our cache translation Okay, mappings are cached in the translation look aside buffer, TLB. It's like the cache for the page tables. Okay, so in a way that I keep the most frequently used table entries inside this TLB, translation look aside buffer, which is very fast because it lives on the MMU. It is very fast, but it's small. Okay, it's like the cache, right? It is small but fast. It's an associative memory. You know this what this means, right? From the organization class, associative memory, which means that it is working like a cache. It maps a value rather than index into another value. You give one value, it maps it to another value, and it is in a very single clock cycle, very, very fast. Okay. If there is a TLB miss, that means that my table entry is not in the cache for TLB. Then all the entry is discarded. A memory lookup is done. A memory lookup will be done. This will be expensive, and the new entry is inserted into the DLB, and the new entry is inserted into the TLB. Okay, and memory lookup is done, and the new entry is inserted into the TLB. So again, this is the same as cache miss. We won't have that many cache misses. Most of the time, whatever I am looking for would be inside the TLB. But if I make a miss, that means that I need to look up that memory, that page number from the memory. That will be expensive, but that's okay because I am not doing this very, very often. Okay, this works because programs tend to exhibit locality of reference. You already know this, right? Locality of reference is the main principle for the cache, the idea of cache. Okay, so on many systems the TLB is managed in hardware. Okay, on many systems the TLB is managed in hardware. On RISC systems, it is explicitly populated by the operating system. So on RISC systems, you know the RISC. What is RISC? Reduced instruction set, right? Reduced instruction set computers. What is the opposite side of, what do we have at the opposite side of RISC?
Complex.
Yes, right, complex instruction set computers. The idea of RISC is that keep your CPU and all related circuitry very, very simple, and handle most of the complexities with the software, with the operating system. So with the RISC systems, this management of TLB is done by the operating system. So that's why we are going to look at a few of the TLB management problems. So remember where we are. Remember where we come to this point. Virtual memory is important. It solves lots of problems. Okay. With the virtual memory, we need virtual memory table. Okay, page table. If the page table is very large, I cannot fit it into the memory management unit. I need to keep it inside the main memory, which is slow. So we came up with a solution, a hybrid solution. Keep the most used table entries inside the MMU, inside this TLB buffer, okay, inside the TLB. And if I have hits all the time, then I am fine. Everything is handled very, very fast. If I have misses, then that's equivalent to cache misses. If I have any miss, then a new entry is inserted into TLB by replacing one of the already used entries inside the TLB. Okay. So most of the time TLB is managed in the hardware, like it's an computer organization problem. But with some systems, it becomes an operating system problem. That's why we are going to look at more carefully to the TLB problems. Okay. Any questions? Remember, there was a slide at the beginning of the semester. It said that with the operating systems, we solve the same problem over and over again. I mean, we are using techniques from the 1960s, but the same problems comes back over and over again. This problem, caching, okay? We use caching in the computer organization class, okay, to close the gap between the main memory and the CPU, the differences, I mean the speed and space differences between the main memory and the CPU. Now we are using the same technique to address the TLB problems, okay, TLB problems. I cannot keep all the page tables on the MMU, so I need to keep them on the RAM, but I need to be fast, so I came up with this solution, TLB solution. Okay, I have a simple TLB table here, a TLB to speed up paging. Okay, so when I get the, remember, virtual address is composed of V and O parts. When I get this virtual page number 140, and okay, I say this is modified, protection is this, and page frame is 31. So among all the possible, maybe 256,000 virtual pages, I only keep 8 of them here. Just 8 of them, because I don't have enough space. Just 8 of them. These are the most frequently used pages, virtual pages. Okay. When I get one of these numbers, at the end I will produce these page frames. Okay. If I don't get a hit, if the virtual page is not one of these numbers, then that means a miss. In that case, I need to go to the main memory, make a main memory lookup, get that number, and replace it with one of the lines here, which would be the least used ones, maybe. It depends on the algorithm. Then continue that way. Okay, and this is the idea of translation local-assigned buffers, which are very, very similar to cache memory between the memory and the CPU. Any questions on the TLB? So, as I said, most of the stuff with the TLB handling, TLB procedures are handled by the operating systems. So let's look at some of the problems. Okay. Software TLB management. Many RISC machines do nearly all of its page management in software. Okay. So that makes the MMU much simpler. Okay. When you handle all of these complexities in software, your MMU becomes simpler. When it becomes simpler, it would make more space for more registers and more caches, which would improve your performance. That's the idea of RISC. Keep everything simple, so that you would have lots of registers, you would have lots of cache, and you would have lots of power. And optimize them, optimize the RISC usage with the software. That's what we are doing with the TLB. Okay. Software TLB management. Soft miss occurs. Okay. When you have a hit, you have a hit. There is no question about it. It's something that we like, and it makes it very, very fast, very, very efficient. When we have a miss, there are different types of misses with the TLB. When you have a soft miss, for example, what does miss means? Miss means that whatever I am looking for is not inside this table, right? That's a miss. That's a miss. So there are two types of misses. A soft miss occurs when the page reference is not in the TLB but is in memory. Okay, you understand this, right? And I need to get a virtual page number. Okay, I need to get a virtual page. Let's say it is not inside this virtual page number. I couldn't find it, so I couldn't get the page frame. So I need to go to the main memory and look for that number in the main memory. Okay, if it is inside that main memory, that page is in the main memory, then it's a soft miss. Why is a soft miss? It says miss for the TLB, but it's not a miss for the main memory page table. Okay, hard miss is that the item that I am looking for is not inside the TLB, and that page is not loaded into the memory. So that means that I need to get that data from the disk. That's very, very expensive. This is a few minutes, this is a few nanoseconds, this is orders of milliseconds. Okay, this is like maybe hard miss is 1,000 times slower than soft miss. So soft miss is maybe 10 times slower than a hit. Okay, TLB hit. But hard miss is 1,000 times slower than soft miss, depending on your disk and that kind of stuff. So hardness is something bad, something bad. What other things that we are going to look at with this software TLV management? A minor page fault, major page fault, and segmentation fault. A minor, what is page fault? Page fault is when I try to, okay, when I try to access some address inside this page. See, it is not inside the, it is not loaded in my physical memory. That's the page fault. So when I try to access one of the addresses inside this virtual page, then something has to be loaded. That means that's a page fault. Okay. So page fault traps to the operating system, and there are a few page fault types. The page may actually be in the memory, okay, when I do the page fault, but not in the processes page table. Okay, the page may have been brought in from this by another process. That means that two processes, one of the processes are using your page, okay, using your page, and the other process needs it, but since the process page tables are different, they don't know that each other, they don't know that somebody else is using that page already. So that's a minor page fault. It's a page fault. The process thinks that it is not inside the memory, but somebody else already brought that memory part to the physical memory. That's called